Okay, today we're going to be looking at transformation of functions. We're going to be talking about three of them: quadratics, square root functions, and the absolute value function. So first we're going to start with the quadratic parent function. And you can see the equation right there. The vertex is at 0, 0. And that is a lot of characteristics. We're really just centering today on transforming them and realizing that they start at home base, so to speak, where the vertex is 0, 0, right there. So really the graph of any quadratic function is the transformation of this parent function. It moves, it always starts, unless you're told otherwise, you're starting at 0, 0, and the movement occurs from there. And please remember, f of x is actually the same as y. You can interchange them. So there are a few different types, and I'm going to go through them. One of them might be a reflection over the x-axis, and that's in green. A different type might be a stretch where the a value is greater than 1. And the last one here I'm putting in is compressions, where a is between 0 and 1, which makes it a fraction. And you can, it's squished down, or the stretch is taller. But where's this a coming from, Ms. Malone? Yes. Well, that's from our vertex form. I've tried to color code it for you so you can see the different things that change. The plus and minus is our reflection. And we're doing reflecting over the x-axis. There is reflection over the y-axis, but we did not cover that in class. And the a value either stretches or compresses. If it's a fraction, it's going to compress. If it's greater than 1, it will stretch it. The h value moves it to the right or left. Remember, the x minus is standard, so if that changes to a plus sign, that means you must have plugged in a negative number. And finally, plus or minus k. So obviously, if it's plus, it's moving up, and if it's a minus sign, it's moving down. Those are the 4 transformations that we've discussed this year. There's only 4 of them. Those are the 4 different movements. So that's the very basic one. It's just a reflection over the x-axis. That would be it. That would be how I would describe the transformation. 2x, what's happening there? Well, if that dotted line is your parent function, the transformed function is going to be skinnier or taller. Choose the adjective that works for you. And we would say that's a stretch by a factor of 2. So there I've written the formula, basically. That's where I'm looking at it. And now comparing what I have with this new equation. I know the vertex is at 4, 2, because h and k are the vertex. A is a positive 1, which is what it is in standard format, so that's not changing anything. If the h is 4, that means we're going right 4 units. Remember, we had to plug in a positive number there. And up 2 units because it's plus 2. So a rough graph of that might look like this. If that's the parent, we've moved it right 4 units and up 2 units. And there's no stretch or compression. Again, describing it in words, right 4 units, up 2 units. That would be it. There's only 2 changes. So let's look at another example. The negative means I'm reflecting over the x-axis. The 2 means I'm stretching by a factor of 2. I'm moving right 1 unit because that's a positive 1 I plugged in, and up 3 units. The vertex would be at 1, 3. So there's the dot. I put it there. Again, this is a rough graph. And I've gone down 2 over 1 to give me those next 2 points using symmetry and made my rough sketch. And it is facing downward because of the reflection. The next graph we're looking at is an absolute value function, which is a perfect V shape. And the vertex form for that is very similar to the other. Notice it has a plus or minus a, x minus h within the absolute value symbols, and a plus and minus k. Fortunately, everything works exactly the same for all of these. So once you understand how they work for any one, you understand it for all. So this is just a little comparison for you again with stretching and compressing. So hopefully you can see how flatter the 1/2 is versus the height of if the a value is 2. Alright, we're going to describe this transformation, and oh, this does look tricky, doesn't it? Because what's that 4 minus? Is that the a, or what is that? Well, don't let yourself get tricked by that. You just have to rewrite it. And yes, I did use a y this time, just to remind you, f of x, and if it has a y in the front, it's the same thing. So now that I've rewritten it and put the plus 4 at the end, that's actually our k value. And the minus sign in front, well, that's a negative a, so negative 1. So we're talking about reflecting over the x-axis. Because it's 1, it's not going to be compressed or stretched. I've rewritten there the absolute value, x minus negative 2, so that you could see that the negative 2 means we are moving left 2 units and up 4. The vertex is negative 2, 4. And there is my rough graph. What about square root functions? Well, that's the shape of them. They start at 0, 0 as well. And of course, those are comparisons again for your stretching in blue or compressing in green. Notice, still the same, plus and minus a. We have an h and we have a k. So if that is the parent function, then what's going to happen? Well, the vertex is at negative 3, negative 4. Notice I'm changing the square root x plus 3 to x minus negative 3, just as a good reminder that that is the h value, negative 3. So let's describe the transformation. Well, it reflected over the x-axis. It stretched by a factor of 2, so I did my best to go from that first little x I made down 2 and over 1. It went left 3 units, and it went down 4 units. And that, ladies and gentlemen, is our last example. If you made it to this slide, you're my math hero. Stay positive and stay strong, folks, and thanks for watching. You all have a great week. Bye-bye.